Hi, I'm Sam Jacobs. This is my capstone project on predicting counter movement jump height from force plate data. So my contributions for this project specifically focused on code-based documentation, connecting the model results to the physics argument, and drafting the actual journal paper. So this project focuses on the counter movement jump, or the CMJ, which is the standard field test for lower body explosive power in sports science. An athlete drops into a rapid counter movement and then jumps as high as they can, and the resulting height serves as a proxy for their performance. Force plates that we use to capture this capture dozens of biomechanical variables per trial, including average force, peak power, phase timings, and squat depth. The problem with this is that many of these correlate highly with jump height, and we don't really have clear guidance on which ones we should actually prioritize in training. So this project aims to address that by directly comparing the two prediction frameworks, relative propulsive net impulse versus peak relative propulsive power. Our data set spans 1,200 trials across 85 participants from 3 different settings. So before I get into my contributions, here's the full arc of how the project got from where I inherited it to where it is now. Uh, Prior contributors Logan Pauser and Tyrell Baker had completed initial modeling and a rough outline for the paper in June 2025, and then work stalled. The codebase and early analysis existed, but most paper sections were still incomplete. When I came on in January of this year, I started by merging notebooks from the Google Drive files provided when I started my project. In week 7, during a meeting with my advisor, we found that this whole drive was outdated. Unbeknownst to both me and the advisor, the repository that I had been giving access to was not kept up to date with the active repository. So when we discovered that, we pivoted immediately. Since then, I audited the full code base, the full up-to-date code base, wrote the README documentation for all 7 project folders, created a gap identification log, and drafted all of the paper sections, generated all of the figures and exported them all into the paper, and connected the model results to the physics argument in writing. So this table shows why the project ended up being more work than originally scoped. The original plan was pretty straightforward. We would work from the inherited notebooks, combine them, and complete the remaining sections, finalize the training and generate the figures, and then get ready to write the paper. This assumed that all of the stuff we had access to was current. So what actually happened was pretty different on almost every row. The inherited notebooks turned out to be the wrong files entirely, which meant continuing from them wasn't possible. The paper sections required original drafting rather than a completion of a near finished draft, and finalizing the model training instead became understanding the pipeline and interpreting the results through the physics argument. So the codebase argument and documentation work, which ended up actually being one of my largest contributions, wasn't even part of the original scope at all. My first contribution was establishing the foundation for the rest of the work to depend on, which is the codebase audit meant reading every script, every data set, every notebook in this inherited repository. This need was demonstrated when we realized that the files I was given access to weren't even the most recent work. It just wasn't documented. From there, I wrote the README files for all 7 project folders, covering every file, function, and dataset column used. The project had no documentation before this, and without it, any new contributor would have had no way to understand what existed or where to start, like I did. I also created a gap identification log. This is a formal document mapping what prior contributors had completed versus what the paper still needed. That log became the roadmap that I worked from. Additionally, I reestablished contact with the prior contributors to coordinate integrating whatever work that they had into the new paper. So my second big contribution is in the interpretation of what the analysis produced and explaining why it came that way. So in this slide on the right, we see this diagonal graph. This is the impulse model, which achieved an R squared of 0.97 versus 0.95 of the power model. What this means is the impulse model was 2% more accurate. This held consistently across all of our seeds and holdout sets. It wasn't just a one seed issue. On the left, we see what this actually means. Our impulse models outperform our power models because we have a direct two-step line from impulse to height. Power doesn't have this equivalent to equation path. It has to travel through work, kinetic energy, velocity, and height, each step introducing variance that of peak value, like peak power, can't capture. Beyond this, the impulse model also uses fewer terms to reach higher accuracy. It's simpler and more predictive, which is a meaningful result. Across all of these timing variables, we also found a parabolic relationship with performance. Best performers cluster near the vertex, suggesting that an optimal push-off duration does exist for each athlete. These findings also held across all of our collection settings and across all of our holdout seeds. My third and biggest contribution has been in writing the journal paper. We drafted up 7 sections: literature review, data collection, tools and software, methods, results, discussion, and conclusion. These all required original synthesis throughout. This wasn't just completing an existing draft, but writing each section from the analysis outward. The model justification work on the right reflects what went into the methods section specifically. Every pipeline decision, whether it's using lasso over ridge regression, or why we used group k-fold rather than standard cross-validation, is explained with rationale tied explicitly to both the statistical context and the domain context. That level of justification was required for what would hopefully become a peer-reviewed paper. All of the figures were grabbed and exported in a consistent visual style for the manuscript, and the results interpretation section does the intellectual work of connecting the R-squared gap to the physics argument. This explains why impulse's direct path to jump height outperforms power, and what the parabolic timing finding shown in the bottom in the figures here implies for how athletes should train. The individual dots on the graph aren't necessarily important, but the parabolic trend they combine to shows this timing performance relationship. I'd like to thank my advisors, Dr. Joshua Gross, Dr. Sam Ogden, and Dr. Eric Martin for project mentorship throughout the semester, as well as initial data collection and conglomeration, and also previous contributors Logan Pauser and Tyrell Baker for the foundational code base that this work was built on, and for additional paperwork and help. Thank you.